Hi, everyone. Thank you all for coming to this talk. I am Nadia Figueroa. I am I'm the newest faculty member that joined GRASP. I joined Penn and GRASP in January of this year. So I've only been here for 8 months. My lab, I'm building it right now. I have several master students working with me. They gave me the keys to my lab like 3 weeks ago, I guess, or 4 weeks ago, and we installed already some robots, and we're doing some cool experiments there. I have 2 PhD students that are joining that are right here in the front. So what I'm going to talk to you about is the research that I've been doing basically from my PhD to now, and some of the ideas and problems that I'm really interested about working on. So that QR code is basically the website to my website, link to my website if you're interested in seeing all the papers, videos, code about everything that I'm going to talk about today. So my work really focuses on building collaborative human-aware robots. So basically, robots that are efficient and adaptive and safe when physically collaborating either between themselves, multiple robots, or a human and a robot. So this is more or less what I like to show this video to explain what collaborative human-aware robots are, right? Here we can see two robots, so two robotic arms and a human collaborating, right? Like the idea is that the robots should help the human grab this large object and place it somewhere else, like stack it on a shelf or move it to another location, for example, in the warehouse or a factory. And here you can see how the robots fluidly adapt and react to the motion of the object that the human wants the robots to grasp from them. So before going into the research, I want to just introduce myself a little bit, my journey, so you understand who I am. So I was born in Mexico, in the very the northest part of Mexico, which is literally like the southest part of the US, which is California. So the border of California and Baja California. Then I went to school. I did undergrad in Mexico, in Tec de Monterrey. I then did my master's in Germany. I worked at the German Space Center during my thesis there. Then I worked at NYU in Abu Dhabi as well as a researcher. Then I went to EPFL and I did my PhD there. So I did my PhD at EPFL. I then did a postdoc at MIT, and then I landed here. So here I am now, faculty and working on collaborative human-aware robotics. So to give you an idea of what level of collaboration means, because if you look at papers that are published in conferences or journals, people use the word collaboration or human-robot interaction for many different things, right? Like for many different kind of like levels of collaboration. So here, this is a very kind of like well-known map, let's say, of the level of collaboration. On the x-axis and on the y-axis is the requirements for safety features and external sensing for that specific level of collaboration. So at the very bottom, you can see the typical industrial robots caged in a cell, right? And the human outside. So that's the least level of the lowest level of collaboration. So basically no collaboration at all. The robot is doing its own thing and the human is doing something else. And there's a physical barrier between the two. Then we have these other two levels, which are the most collaborative applications that we see today in industry, or maybe like in other setups, for example, coexistence, where there is no more fence, but the workspaces are not shared, right? So like the robot is doing something, is doing a task, is manipulating an object, polishing things, picking things from a table in its own workspace, and then the human has its own workspace, but they're not overlapping. And then we have sequential collaboration within the same red box, where the robot now and the human, they do share some of their workspaces are parts of the workspace are overlapping, but the motions are basically sequential. So the robot does something on a part, and then it moves away, and then the human comes in and does something else. For example, let's say inserting, doing some sort of insertion task, like when building some electronic components, that the robot has to place the parts, and then the human comes in and does the wiggling or something like that to like insert the parts. So that's called sequential collaboration, and that's what we see today. That's what we have in industry. Then there's another higher level, which is now cooperation, right? Now the robot and the human are basically manipulating the same parts at the same time, right? Both in basically at the same time, but at the motion level, right? So like they're cooperating on the same parts. But now the highest level is responsive collaboration, right? Where the robot actually responds in real time to the movements of the human. And that is what collaborative human aware robotics is. And that's the level of collaboration that I am really interested in. How can we get there? How can we get a robot? How can we build robots that can responsively collaborate with humans while being safe, while being efficient, and being able to have this kind of like fluid interaction, basically how two humans interact, how two humans collaborate. So that's what collaborative human aware robotics means to me. And that's what I'm really interested in developing. And that's what I've been doing basically since my PhD. So this whole idea, obviously, I mean, this is very much plays kind of like in the industrial context, but this also applies to not only industry, but for example, factories, warehouses, in the workplace, also household activities, right? Like we would want robots to help us peel vegetables or do these type of like repetitive tasks that we don't really want to, like we have to do because that's part of the process of cooking. But we don't really, like if we had a robot that did it for us, I'm pretty sure that all of you would have the robot do the peeling and then you guys do something else, like the human will be the creative chef in this point and then just figure out how to mix all the ingredients, whereas having to actually do all of these manual repetitive things. And then obviously there's also, so in the top row of video, you see kind of like just these applications where the human is teaching the robot how to do these things, but then also what we care about is now the robot collaborating with the human, right? Like having the robots really be responsive and be able to interact and collaborate with the robot in a very fluid manner without having to stop and then plan and then stop and then plan. So like basically they have to react whenever the human is moving, whenever the objects are moving. So these are more or less kind of like the two, let's say, overarching applications that I really like to focus on how do we learn from humans then, right? So like, so when we go to, for example, a cooking class, the teacher is right in front, the chef is in front of us, and they're teaching us how to do certain parts of the recipe, and then we do it. And then if we try, if we fail, the teacher comes and then gives us some corrections so that, and then we start refining the skill, right? So what I really focus on in my research is trying to understand how this mechanism works for learning from demonstration, and then being able to correct the motions or the tasks that we learn from the demonstrator. And then also collaborating with the human, obviously. So once we know what the task is and we've learned it from the human, how can we collaborate with them? So the research that I do, basically developing these collaborative human aware robotic systems, is very interdisciplinary, right? So like I take inspiration from psychology, human behavior modeling. We do a lot of we use a lot of tools of machine learning, control theory, to be able to control the robot as a feedback, so, as a feedback control system, not open loop and just let it go, because here what we need is reactivity. And the only way that we can get reactivity is by controlling the robot in closed loop. Otherwise, like how can we make the robot react if it's not processing all the information from the sensors and then being able to plan it? So a lot of so obviously we need to understand how the robot is modeled, robot control, kinematics, dynamics. Perception is also a big part of that I'm currently working on with my students, on how can we integrate perception, noisy perception, faulty perception within these reactive type of control techniques. So let me see. All right. So within this now that I kind of like explained that what's my goal in my research, this collaborative human aware robotics, and where I draw inspirations from, I always like to outline kind of like the 3 objectives that one needs, right? So if we want to reach that highest level of collaboration, there are 3, from my point of view, there are 3 clear objectives that we need to look into in order to actually achieve that. So the first objective is efficient teaching. So we need to minimize the time and effort it takes the human to actually transfer a task to the robot, for the robot to actually understand what the human wanted to do. Oops, let me see. Then we also need adaptivity and reactivity, right? It's like if we can have a way to efficiently teach the robot how to do a task, how to model a task, then what we want is like whatever model that the robot has learned from the human, it should be able to adapt. For example, if you teach the robot to polish, let's say a fender or the door of a car, let's say in one certain configuration, and then suddenly you change it, you shouldn't need to give the robot another demonstration to do that, right? Like the robot should be able to understand that the task is to go towards that surface, apply a certain amount of force, and change its compliance based on the surface, and then continue. But the current state of the art doesn't really allow for that, right? So we need to come up with new algorithms that are capable of learning with the efficiency, so least amount of data as possible, least amount of time for training as possible, but at the same time being able to react and be able to adapt to changes, because these robots are going to be working in human-centric spaces that are uncontrolled, right? Like it's not a factory where we control everything. Once you put the human in the loop, once you put the human in the workspace of the robot, then it becomes very difficult. And we need to be able to react and adapt. And then, of course, we want to guarantee safe interaction. So we want to guarantee that the robot will always be safe around the human, and that the robot will always be safe with itself. So not collide with itself, with its own links, not collide with the environment. So these are kind of like the 3 objectives: efficiency, adaptation, and safety. Oops. Okay. So if we just look at the last 2, so adaptation and safety, that's where I draw a lot of inspiration from control theory, right? Because we can guarantee, we can put guarantees on whatever model or whatever behavior that we want the robot to do using control theory, using for example, stability theory, ensuring convergence, being able to do feedback control systems in a robust way. And the efficient teaching part, obviously, machine learning. We can take some inspiration from there. Now, obviously, this is not like a novel idea of how using machine learning to teach robots. Yeah, I mean, that's what a lot of people have been doing in the last 10 years. But if you think about, for example, here this picture is of the Google farm where they had like hundreds of KUKA robots figuring out how to grasp this different types of objects, training for weeks to do that. And of course, that we cannot rely on those type of learning paradigms when we want the robot to learn from a human in a very fast way, and we want it to adapt. So some of the limitations is that we need to do model selection. It takes a lot of data and training from hours to days just to train the robot to grasp an object, where you can come up with a controller that does that in less amount of time. Obviously, the other problem is the robustness to changes. So maybe a lot of you have heard about this covariate shift or distribution shift problem, where if you teach a robot, if you give a neural network, for example, a whole bunch of data to learn a policy, to follow a trajectory, but then it goes away from that region in the state space, then you don't know what that motion policy is going to do, right? Like you don't know what it's going to do. So in these cases, these don't work in the context of human aware robotics. These let's say unconstrained models don't work, because we need to ensure some sort of stability. We need to ensure some sort of safety and boundedness on the policies that we're learning. And obviously there's always this kind of like trade-off between reproduction accuracy of the trajectory of the motion that we want the robot to learn, and these convergence guarantees. So overall, this is kind of here you can see kind of like the three, main objectives that I really focus on in my work, which is efficient learning. So how can we teach a robot, for example, to do this inspection task with simply 2 demonstrations, instead of having it exploring a reinforcement learning setup for hours or days to do that, when you can actually just bring the expert and take that knowledge from the expert, learn a model from that, and then have the robot reproduce it. And then obviously adaptation as well, right? Once in this case, we taught the robot how to follow this line, this curve on the floor. But if we perturb it, then it knows that it allows for that perturbation, but it goes back to the track, right? And so that's kind of like what I think about when I say adaptation. So like the robot, the model that was learned should be able to adapt to these changes or these perturbations. And then obviously safety, right? So if the robot is doing its own thing, it's following the trajectory that it was taught to do. How can we ensure that if the human comes in, then it will basically not collide with the human? So obstacle avoidance, collision avoidance, but collision avoidance with dynamic obstacles. In this case, the human is a dynamic multi-body obstacle, so it becomes a little bit more difficult than just avoiding a sphere, right? Wait, there's one more video. Nope. Oh, it's not making it. Yeah, I wanted to have it full screen, but it's not. I mean, you can see it there. So here is basically collision avoidance, but now with multiple robots trying, like, avoiding colliding with themselves while tracking the motion of the human. In this case, it's tracking kind of like 2 rigid bodies that we mounted on the human's wrist. So this is going to be the only like real technical part, and it's not even that technical, but just to give you an idea of how I can of the way that I achieve this in my research is by using these kind of like dynamical system-based learning from demonstration approach, right? That's how I merge machine learning with control theory. So here we assume that the motion of the robot, in this case, let's just be very simple, and the end effector motion, right? Like x is the position, x dot is the velocity of the end effector of the robots. And what we do is we model that desired motion of the robot as a first order differential equation that is subject to kind of like convergence and stability constraints. So basically this function f of x gives us what's the desired evolution of the state variable x, right? So basically if the robot is here, it'll follow those lines. If it's perturbed, it'll continue following the integral curves of this vector field. And this we can actually learn from demonstrations if we formulate the policy or the machine learning algorithm in such a way that basically the policy that we learn is this first order differential equation, and we impose constraints. So convergence stability constraints, either through Lyapunov theory or through contraction theory, which is one of the more kind of like novel ways that people are doing it now. And one of the cool things about this is that because it's let's say instantaneous controller, it will adapt on the fly, as you can see here, where where we basically parameterize the dynamical system for 2 arms to follow a flying object, right? Which is super fast. So we can throw the object to the robots, and then the robots will adapt. And here you can see how even kind of like each of the 2 robots are adapting to different points, different grasping points on the flying bar. Another cool kind of like advantage of this approach is that it's kind of like inherently robust to kind of like these what I call adversarial perturbations in this case. So like the robot is trying to release the block in the release station, but then the human is just perturbing it. If you think about the vector field that I showed you before, what's happening is basically the robot is reaching the attractor, and then it experiences a perturbation. But then there's like, it allows that perturbation. The way that it allows is because it's a torque control robot, it's using a compliance and control strategy. So that's why the perturbations are allowed, but there is no error being integrated because our motion policy is basically a first order dynamical system that's only state dependent. So we're not really kind of like integrating any error or anything like that. And then we can have other types of adaptation, which are more kind of like intentional, right? So here, for example, the robot grabbed the blue one, but I said, no, I actually want you to inspect the red one. And you can come and interrupt the robot and do that without any planning, without any, other high level planning architecture that allows you to do this. So it's inherent basically in the motion policy already. So that's one of the cool things about this approach. So as you can see on the bottom right, if you give it demonstrations, which are these like red trajectories, and if you formulate the learning problem as like learning this a dynamical system basically of the motion, of the desired motion, then we can achieve these really, really cool behaviors inherently already like in the motion policy. So here I'm just showing some videos of different types of tasks that I have taught the robots to do, like with these type of formulations. And as you can see, it's quite broad. It's not just like a very, obviously there are some assumptions, there's only one target, but the trajectory that the robot is doing is quite nonlinear. So you can represent like quite complex trajectories with a simple system. And then here you can see how this same strategy can be applied to control any type of robot virtually, because it's just that we're just controlling for the Cartesian trajectory. In the first videos that I showed you, it was the Cartesian motion of the end effector of one robot or two robots, but then you can control, for example, a humanoid. With the humanoid, those who do work in like locomotion, you know that it needs a reference velocity. That's all it needs. So the dynamical system is basically giving the reference velocity to the robot, and then the low-level controller kind of like follows that. And for the wheelchair, you can see the same thing. And then you can even see that two robots, if the dynamical system is controlling the motion of the coupled system, basically of the box, then you can achieve those type of behaviors even like with the multi robotic system or multi-agent systems. So these are some of the things that I'm really excited about, that I work on. Obviously, some things are missing. For example, integrating perception. So in all of the works that I showed you, we are tracking the objects, but we are assuming that we have perfect knowledge of the objects, basically using the OptiTrack, right? Which is not very realistic if we want to actually use these robots in the real world. So we need to be able to now couple these kind of like reactive policies with perception, and then once we do that, then we have to deal with uncertainty, right? Because we cannot assume that every perception system will be perfect. Actually, I think we should assume that every perception system is not reliable at all, and that it will give you, it'll actually fail sometimes. So how can we then develop some sort of strategy to already account for that? So we know that if suddenly we see an object and then it's occluded, but it's occluded by a human, and then suddenly it appears somewhere else. So we can be able to create some sort of knowledge of like, okay, as a human, we know that because we have object permanence, right? We know that when an object is occluded, then it's somewhere behind it, behind the occluder. So how can we introduce those type of ideas into this pipeline so that we can really be able to use these type of reactive strategies in the real world? And then also obviously exploring adaptive and online learning, kind of like to shape these motion policies, because obviously we don't, if we learn them from just a single demonstration or a single batch of data, that might not really show you the entirety of the task, right? So like if we can introduce an algorithm that can be able to incrementally learn all of the entire task while guaranteeing all the constraints, that would be amazing. Yeah, so and then the third kind of like a topic that I really like is, oh no, wait, yeah. So I forgot about this part, yes. So what I showed you before was adaptation, what I call adaptation at the motion level. So it only adapts to kind of like these perturbations that the human is kind of like artificially applying to the robot. But what happens if now the task is that the robot should scoop, let's say, beans, the red beans from one bowl and place them on the other, right? So at the so here in the second video, you can see that the motion policy, it's reactive at the motion level at these perturbations, but it has no idea that it could actually drop the beams, right? Because it's only dependent, it's only reacting to the state of the robot, not the state and some sensor, or it has no idea of what it's really doing, like at the high level task, right? So you can see there on the right. So there was so basically it fails. Like if the perturbation is really is large enough and it's adversarial, then basically it fails. So here the idea is that these policies, they're not like, what we want them is to be generalizable and adaptable, but they're bounded, right? Like it's not like we cannot really know exactly what the robot should do everywhere in the state space by a single demonstration. But we could bound it if we know where it fails. So that's kind of like the idea that we developed here. And so this we call it LTLDS because we actually use a linear temporal logic formula to kind of like represent what the actual task should be. And then we introduce that formula, which becomes now kind of like a hybrid system where we are switching between different motion policies. So here you can see that the robot fails there. It fails when it goes to that state, but then it learns from that failure. So it starts bounding the motion policy, and if it's led to that state, basically the robot knows that it failed to drop the beam, so it goes again and scoops them instead of just following the path that it thinks it should do. So that's kind of like the idea of introducing this kind of like adaptation now at the task level, where we are now tracking a sensor state as well, not just the state of the robot, but also the state of the object that we're trying to transport or that we're trying to manipulate, for example. Here, I want to show you this video that I actually recorded last week for a paper submission. So here you can see that the initial kind of like a policy that has no knowledge of the sensor state. In this case, is that the cube should go through the inspection line, right? And there you can see that with small perturbations, it still finishes the task. Like, so these are what I call in distribution perturbations. So you perturb the policy, but it still stays within the region where you gave the data. So in this case, we gave us like 2 expert policies. But if you perturb it far away from the distribution, then you see that the robot will just follow the dynamical system that's just leading you towards the target, because that was the only guarantee. That's the only guarantee that's being imposed on this motion policy. But now if we introduce the specification of the task, where here we specify that, okay, the robot actually has to follow those trajectories, but also that cube always needs to be seen by that camera, then which is the sensor state that we're introducing, then now the robot knows that if it's pushed towards the boundary of that kind of like of that mode, then it goes back and does the scan, because it's now reacting to these task level perturbations where the human is basically leading the robot to fail, but then the robot notices that it failed, so it goes back and does the same thing. And all of this was basically learned by an offline approach where you teach the robot what the motion is, and then we perturb it. We do some like random perturbations to teach the robot what the failures are. So it's kind of like an offline learning, but then we also have an online learning step where we kind of like learn these boundaries. We learn what the boundaries of the motion policy are. And yeah, so that's kind of like one that was one example of adaptation that I'm really interested in, is how to introduce this task level adaptation. And then another type of adaptation that I'm really interested, let's see, okay, 2 minutes morning, when was that? Okay. Yeah, so the other type of adaptation that I'm really interested in is, so the videos that I showed you before of this task, I like to call this the adaptation, but only at a kinematic level, right? So where the robot is just moving towards the human is moving towards the robots, and the robots are just adapting their motion. But what if we want but what if we wanted something like wait, it's not here. Something like this, right? To where we want we want multiple humans and multiple robots to dynamically adapt and lift and move this large couch, you know, like through very highly constrained environments, right? Like, and if those of you who can identify where this comes from, it's from Friends, like a very famous episode of Friends. There, Ross is yelling pivot, pivot to the other humans, but the other humans have no idea what pivot means. So then they fail. They fail in the task because they don't have the same knowledge. So how can we now introduce? How can we come up with some strategies for robots to actually adapt, to understand what the human is, what's the intention of the human, and how to accomplish the task correctly? I'm already out of time, right? Okay. Okay, so I'm just, yeah, it's fine. I'm almost done. Let's see. Okay. So yeah, I mean, so I just missed the part about safety, but you already saw some videos of that I showed. So here is kind of like the summary. These are the 3 really important problems that I'm interested in: how to provide safety in human-robot interaction or robot-robot interaction. How can we provide adaptation at different levels: motion level adaptation, task level adaptation, and also adaptation to changes when we have multiple robots, and how to make learning as most efficient as possible. And the applications are also endless, right? So we can apply these 3 kind of like objectives applied to problems in industry, in the household, and also in rehabilitation robotics, which are what some of my PhD students are going to work on. Yeah, so quickly, so you guys know, I teach MEME 520 Introduction to Robotics in the spring. And in the fall, potentially next fall, I'm going to teach all about the type of work that I do, which is from my textbook that was published last year on learning for adaptive and reactive robot control. So it's going to be a new course about all the foundations on reactive and adaptive controllers. I'm not sure if it's going to be ready by the fall, but it might be. So look out for it if you're interested in this type of research. And just these are all the collaborators that I worked with on the videos that I showed you today.